Section 4.1, Exponential Growth and Decay. First, we're going to talk about exponential growth. Exponential growth occurs when, during each time interval of a fixed length, a dependent variable is multiplied by a certain constant amount, which we're going to call b, and this value of b will be greater than 1. B will be referred to as the growth factor. The way exponential growth works is we'll start off with an initial amount of a substance or a population, which we're going to call p sub 0. And we're going to fix a period of time, and we'll call this time 1 unit. When 1 unit passes, our population is going to grow by a factor of b, which means we're going to take our initial value and multiply by b, and we get p sub 0 times b, and that would be our population after 1 unit of time. Well, when another unit of time passes, we would multiply the b sub 0 times b by another b, and we get p sub 0 times b squared. And for each unit of time that passes, we're going to multiply b again and again and again. So with b being our growth factor, which is what we're multiplying when 1 unit of time passes, our model for our exponential growth will be p of t equals p sub 0 times b to the t. In this example, a population of 24 turtles quadruples every year. We're going to write a formula for the population of the turtles after t years. How can we tell that we should be making an exponential model and not, say, quadratic or linear? To understand why we're going to use an exponential model here, let's look at various times and calculate what our turtle population would be. We're told at the start, which means t equals 0, there are 24 turtles. We're then told every year the population quadruples. If we go to the next year, which would be t equals 1, we know the population is supposed to quadruple, which means we'll take last year's population, which was 24, and multiply by 4, and we would get a population of 96 turtles. How would we figure out the population next year? Well, again, every year, the population is quadrupling. So to calculate, we would multiply last year's population by 4. And the same thing goes if we were to calculate year 3. We would just multiply last year's population by 4. And we would keep multiplying by 4 each year as we go. This is the characteristic of an exponential growth problem. To get to the next time, we would multiply by our growth factor. So to write our formula, we want to identify our initial population, P0, and our growth factor, B. And the problem, they tell us we start with 24 turtles, and they tell us our growth factor is 4, so B will equal 4. So using our model, our population P of T will equal our initial population, 24, times, and for exponential growth and later decay, I am going to put a dot for multiplication, so that way we don't make any confusions with the base of our exponent. Then our growth factor 4 raised to the t power. Now, how many turtles will there be after 5 years? Well, t is how many years that pass, so t will equal 5, which means this problem is asking us to find p of t. So if we take t, plug it in to our formula that we found in the first part, we're going to get 24 times 4 raised to the 5th power, which we could use a calculator to evaluate. In fact, the calculator would be highly suggested because 4 to the 5th can be a really large number. Going into Desmos, we'll type in our equation, and there we have p of t equals 24 times 4t, and we'll evaluate p of 5, and it tells us there'll be 24,576 turtles after 5 years. Notice how fast our population is growing. From a start of 24 turtles, in just 5 years of quadrupling our population, we grew to over 24,000 turtles. One of the key characteristics of exponential models is how quickly it can grow. If we zoom out, notice how this line is getting steeper and steeper. With exponential growth models, it may start off growing slow, but then it hits a certain point and it kind of just takes off where that growth is extremely fast. And you may have heard in common description the phrase growing exponentially to represent a very fast growth. And that's why we use that phrasing, because exponential growth is very fast, and it's even faster than linear growth, where we're just adding the same value over a fixed period of time. Recall from the definition of exponential growth that over each fixed period of time, we're multiplying our dependent variable by some factor b, and b was greater than 1. What would happen if we make b between 0 and 1 instead? When we decide to make b between 0 and 1, we no longer have a growth. What we're going to have instead is a decay, more specifically an exponential decay. Exponential decays occur when during each time interval of a fixed length, a dependent variable is multiplied by a certain constant amount, and this constant amount will be between 0 and 1. So the definition of exponential decay is almost exactly the same as the definition of exponential growth. The only difference is the size of our factor. In growth, our factor is greater than 1, which at that point we call it a growth factor. But for exponential decay, our factor is between 0 and 1. And when you multiply a value by a quantity between 0 and 1, it's going to make that value smaller. Since the value is getting smaller, in other words, decaying, we're going to refer to b as the decay factor when it's between 0 and 1. As far as modeling exponential decay, it's exactly the same as the model for exponential growth. It's still the p of t equals p sub 0 b to the t. P sub 0 is still the initial value, and b is the factor that we're multiplying over and over again. But this time, it's between 0 and 1. In this example, a 50 milligram sample of a substance decays by a 10th every month. Since we're told that our substance decays by a 10th every month, we're dealing with an exponential decay problem. That's because my substance is losing a 10th of itself every month. So to make our model, P of T represents the amount that's left, and we know that's going to equal our initial amount times our decay factor raised to the T power. Now our P of 0, which is our initial amount, is 50 milligrams, which was given to us in the problem. But we have to be very careful with the value of B. We are told here that our substance decays by a 10th, which means our sample is losing 1/10 of itself. Well, recall P of T represents how much is left. So our B is not going to be 0.1, like we would initially just quickly read the problem and think it would be. It's actually going to be 1 minus 0.1. 1/10 represents the fraction of our sample that's going away. Because P of t represents the amount we're keeping that hasn't decayed away, we're going to do 1 minus 0.1 to represent what fraction of the sample we're actually keeping. So our B here is actually 0.9. Because again, 0.9 represents the fraction of our sample that we're keeping, whereas the 0.1 represents the fraction of our sample that's leaving. So our function P of t is going to equal 50 times 0.9 raised to the t power. So again, be very careful when reading decay problems. Oftentimes, they tell us what fraction of the substance is going away or decaying away. Typically, we're going to do 1 minus that value in order to get what fraction of our substance remains. Next, they want to know how much of our substance will there be after 2 months, meaning we're trying to find P of 2, which if we plug in will be 50 times 0.9 squared. And we could punch this into the calculator, or we can go into Desmos, type in our function, and then we can type in P of 2 in the next line. And we get that there would be 40.5 milligrams of our substance left after 2 months. Notice in the graph for decay, as we see here from the function we graph P of t, out here we can see that our exponential decay model decreases as t gets larger. And it does get closer and closer to 0, but will never cross 0. That's because there's always going to be a substance there, and that substance will just keep losing substance, but it'll never actually completely go away. There'll still be a little bit there that will still be able to decay. In the last example, we weren't directly told what the decay factor was. Instead, what we were told was a decay rate, which is a fraction that our substance is decaying by. Whenever we see decay rate, or something that indicates a rate of decay, we know we're going to be dealing with an exponential decay problem. If we let R be the decay rate, our decay factor B is going to equal 1 minus our decay rate, which is precisely what we did in the last problem. If R represents the decay rate, which is the fraction of our substance we're losing, then B equals 1 minus R would represent the amount of our substance that we're keeping. One thing to keep in mind, we may see the term percent decrease instead of explicitly saying decay rate, but if we see percent decrease, that is also indicating an exponential decay. Keeping in mind that B equals 1 minus R, our model can be modified to P of t equals P sub 0 times 1 minus RT. We can also do something similar with growth rate. The growth rate, which indicates an exponential growth, is a fraction of our substance that we're gaining on top of our original substance. If R is the growth rate, then B equals 1 plus R would be the growth factor. R represents how much of our substance we're gaining. 1 plus R would represent the amount of that substance we're starting with plus the fraction we're gaining. Remember, if we are given a percentage, which would be indicated by a percent increase, remember to convert that percentage to a decimal. Using the fact that B equals 1 plus R would be our growth factor, our model would be modified to P of t equals P sub 0 times 1 plus R to the t. Now, this formula should look familiar to you. Back in a previous unit, this was our formula for compound interest. So compound interest is an example of an exponential growth, where the rate at which the interest is accruing would be an example of a growth rate, not a growth factor. So be very careful with the difference between a growth or decay rate versus a growth or decay factor. Speaking of compound interest, let's revisit what compound interest is, just as a refresher from our previous unit. Compound interest is where new interest is earned upon interest that we've already accumulated. And this is a classic example of exponential growth. Another way to think about exponential growth is whatever we gain through the growth process also accrues additional gains. If we have compound interest that is compounding annually, recall that our formula is A equals P times 1 plus R raised to the t. P is our principal, our starting amount. R is our interest rate, which is usually represented as a percentage. R, thanks to what we just learned, would be an example of a growth rate, because that is the rate at which we are growing. 1 plus R would then be our growth factor, because that's what's being multiplied to our previous amount to get our new amount each year. T is time, which here time is going to be measured in years, and A is going to be the amount of money after T amount of time has passed. And keep in mind, this would be the principal plus the interest we've accumulated. Now we're going to take a look at a few functions and determine whether these functions model an exponential growth or decay. Then we're going to determine their growth or decay factor or their growth or decay rate. We're also going to determine what the initial value of the function is. Looking at f first, the way we can tell whether we're dealing with a growth or decay is based off the size of the base that is being raised to x. Since 5.2 is bigger than 1, f of x would be an example of an exponential growth. Now, what would be the growth factor and what would be the growth rate? Well, our growth factor would be the value of b, which equals 5.2. Now, for our growth rate, which we're going to call r, recall that our growth factor equals 1 plus our growth rate. Well, if we manipulate this formula by subtracting 1 from both sides, we get that our growth rate equals our growth factor minus 1. But we've already determined our growth factor to be 5.2, and 5.2 minus 1 is 4.2. So r is 4.2. Lastly, what's our initial value? Well, our initial value would come from what's in front of what's being raised to the x power, which here would be 800. You could also calculate this by plugging 0 in for x. 5.2 to the 0th power would be 1. 800 times 1 would be 800. Now, moving on to g of x underneath. To determine if it's a growth or decay, we'll look at the base of what's being raised to the x power, and we see that's 0.45. Since 0.45 is less than 1, this function would represent an exponential decay. Well, what would be our decay factor, which is b? Well, that's the base of what's being raised to the x power, which is 0.45. Next, what is our decay rate, which is r? Well, recall that when we're working with an exponential decay, the relationship between the decay factor and the decay rate is b equals 1 minus r. Well, if we manipulate this by adding r and subtracting b from both sides, we get that r equals 1 minus b. Since we've already found that b is 0.45, then r equals 1 minus 0.45, or 0.55. Next, we want to know the initial value. Our initial value would be what's in front of what's raised to the x power, which here would be 92.4. We could also get the 92.4 by plugging in 0 into our function. Next, let's take a look at capital F of x. Again, determining if it's a growth or decay, looking at the base of the exponential expression, 0.6, which is smaller than 1, which is a decay. So we'll find the decay factor, which is our base, which here would be 0.6. For the rate, well, recall from the g of x example, which was also the decay, we had the relationship that our decay rate equals 1 minus our decay factor. Since our decay factor is 0.6, then r equals 1 minus 0.6, which is 0.4. And what's our initial value? Well, taking a look at what's in front of the 0.6, we see that that's 2. So our initial value is 2. Next, capital G of x, looking at the base to see if we're working with an exponential growth or exponential decay. Since 10.23 is bigger than 1, we're dealing with an exponential growth. Now we'll find our growth factor. Well, our growth factor is the base of our exponential expression, which is 10.23. As for the growth rate, recall from the first example we did on this slide that we found the relationship between the growth rate and the growth factor can be rewritten as r equals b minus 1. So our growth rate equals our growth factor minus 1, so r equals b minus 1, which means r equals 10.23 minus 1, which equals 9.23. And lastly, for the initial amount, that would be the value in front. So our initial value would be 4.234. In this example, I invest $20,000 into a savings account that earns 4.5% interest that compounds annually. First, we're going to write an equation that represents how much money will be in our account after 2 years. So thinking about our compound interest formula, we're told the value of our principal, which is our starting amount, is $20,000, and we're told our annual rate, R, is 4.5%. But remember, we don't work with percentages. Always convert them to decimals by dividing by 100. And we get that R is 0.045. Now we have everything we need to write out our formula. The amount of money in our account A is going to equal our principal P, which is 20,000, times 1 plus our growth rate of 0.045 raised to the T power. Note that since the only variable on the right-hand side is time, we just wrote A as a function of time. So we're going to put this in function notation, replacing the A with A of T. That way we can use Desmos to help us with our other questions. Our next question is how much money will be in our account after 20 years? Well, 20 years is a value of time. How much money is in our account is represented by A. So using function notation, we're trying to figure out what A of 20 will be equal to. To make this easy on ourselves, going to Desmos, we'll type in our A function, and we have 20,000 times 1 plus 0.45t. And since we're using the function notation to evaluate A of 20, we just need to type in A of 20 into Desmos. And we get that there will be $48,234.28 in my account after 20 years. Next, how long will it take for the account to grow to $100,000 if I do not make any withdrawals or deposits? Well, since A represents the amount of money in my account, I'm trying to solve the equation A of T equals 100,000. So going into Desmos, I want to get rid of the A of T, and I want to put in Y equals 100,000. Now, currently nothing is showing up, so let's zoom out, and we can see the point of intersection between the green line, which represents Y equals 100,000, and our blue graph, which represents our function for the amount of money in our account, intersects at the point 36.5641, comma, 100,000. Since they're asking for when, and the first component of these order pairs would be time, the solution to this equation would be T equals 36.6 years. So after 36.6 years, I'll have $100,000 in my account. You bought a new car for $40,000. The car loses 5.2% of its value every year after purchase. We're going to write an equation that represents the car's value T years after purchase. Now, taking a look back at the problem, because they're telling us the car loses 5.2% of its value each year, we're dealing with an exponential decay. And this 5.2 won't be a decay factor, it's a decay rate, because it's telling us what percentage we're losing, not what percentage we're keeping. Decay factors tell us the percentage we keep, or the fraction. So to write our model, first we need to identify our initial amount, which we're told in the problem the car cost originally $40,000, and we want to know our decay rate, which is R, which is 5.2%, which converted to a decimal by dividing by 100 is 0.052. Since we're given a decay rate, we're going to use the version of the model P of T equals P sub 0 times 1 minus R to the T, which means P of T equals 40,000 times 1 minus 0.052 raised to the T power. And to simplify that just a little bit more, we can do the 1 minus 0.052, and we get P of T equals 40,000 times 0.948 raised to T. Next, how much will the car be worth after 5 years? Well, since they're asking for how much the car will be worth, which we're using P for this time, and we're doing this for 5 years, which means T would be 5, so we're trying to evaluate P of 5. Going into Desmos, we can type in our model, and now that we have our model typed in, we can evaluate P of 5. and we get that P of T would equal $30,626.80. What this means is our car loses almost $10,000 in value in just 5 years.